welcome again to the new lecture of this course, Solar Photovoltaics Principles, Technologies and Materials. So, we will just do a brief recap to begin with and then move on with the remaining part of the lecture. In the last lecture we talked about CIGS or copper, indium, gallium selenide solar cells. And these materials, this is an interesting material because by changing the ratio of indium to gallium, one can tune the band gap. And this material, again it has a similar structure to CDT solar cells, and CIGS layers, as we saw in the last lecture, can be formed by various processes including evaporation, sputtering, closed space sublimation, and then also using chemical processes such as CVD, I think we looked at the two-step processes, basically two-step process where you deposit the metal layer first and then followed by their selenization. So, metal deposition followed by selenization. And in these solar cells, selenization is a very important aspect because selenium vacancies, the deficiency of selenium can lead to poor devices, and which is done at about 400-500 degrees centigrade, which is a fairly high temperature. And and one can also do these by spray pyrolysis, etc. As well as chemical bath deposition, So, these are various processes through which you can deposit CIGS. We have looked at evaporation, we looked at two-step process in some detail, and the remaining processes are well understandable. Sputtering we have discussed in case of CDT, which is fairly similar in this case also. So, all you are going to need to have is 4 targets of one of cadmium, copper, one of gallium, one of indium, one of selenium. So, gallium of course is not present in, it is a metal which is in liquid form. So, it has to be at room temperature, it is in liquid form. So, you have to sputter it from a compound source. So, as a result, sputtering may require to be done from the compound sources, and then of course, when the plasma species reach the surface of the substrate, they react and form the compound. So, these are various processes by which you can synthesize CIGS. If you look at CDS deposition, CDS can be deposited by chemical bath deposition. Essentially what you have here is basically you have aqueous solution with salts of cadmium, such as cadmium and sulfur, such as cadmium sulfate. You can have cadmium chloride as well, and you can have cadmium iodide, etc. So, these are the salts of cadmium acetate, etc. And in these, so this is a cadmium salt. Then we use a complexing agent of ammonia, and then sulfur source is essentially thiourea, that is SCNH2 twice. And these are basically deposited, these are basically stirred in a chamber, and then you put a substrate there, and on this you can deposit at a certain temperature, and temperature is about 80 to 60 degrees centigrade. So, at this temperature the reaction occurs, and the reaction rate can be controlled by things like temperature and concentration of the salts, and that you have to optimize, and this leads to deposition of cadmium sulphide. This is also valid for, by the way, cadmium telluride solar cells. So, the reaction that takes place is CdNH3 2 minus plus ScNH2 2 plus 2 OH minus, they give rise to CdS plus H2NCN plus 4NH3 plus 2 H2O. So, essentially using these two you make a complex salt of cadmium and ammonia. This is thiourea, this is from water, and this gives rise to your cadmium sulphide, which is the final compound. So, this is the method of growth of CDS in CIGS solar cells. Now, the important thing in these solar cells is the role of interfaces. So, since you have first is the growth of CDS. So, CDS is something which needs to be grown in sort of pseudo epitaxial manner. Pseudo epitaxial means epitaxial would mean nearly single crystal films, okay. So, which means all the regions in the film will be at the same orientation. Pseudo epitaxial will be sort of nearly close to being epitaxial, but not quite there. So, it is somewhere between polycrystalline and single crystal films, sort of textured films. And what happens is that in these cases CDS, so if you have CDS next to CIGS, CIGS is copper, indium, gallium, Se2. The problem that happens is that you tend to have at the interface accumulation of CDSE. This tends to accumulate at the interface, and this also tends to reduce the performance of the solar cell. So, this can be an issue in these solar cells, and we need to avoid this by designing appropriate temperature, and CDS also has since it is a cadmium sulphide is a wide band gap semiconductor with a band gap of 2.42 eV. This leads to some absorption loss in the cell current. So, there is a little bit of question of absorption losses in the short wavelength range. So, people have tried to look for alternatives of various CDS, things like things like zinc, tin oxide, indium selenide, etc. They have been researched to look for an alternative towards forming even zinc magnesium oxide, ZnMgO. So, these have been tried to replace CDS. However, CDS is the most used material in case of these films. The other materials, so if you look for transparent electrodes in these cases, so transparent electrodes generally we use indium tin oxide or tin oxide, doped tin oxide or zinc oxide. So, these are transparent electrodes which should be conducting, okay. So, these are all conducting forms. So, the composition is such that they are conducting. They are generally made by either sputtering or evaporation or ALCVD, that is atomic layer chemical vapor deposition. The sheet resistance of these electrodes in the cells about 20 to 30 ohms per square. So, RS of electrodes, whereas in modules already have parasitic losses. So, resistance is lower, which is 5 to 10 ohms per square. The buffer layers are generally, So, on top we use buffer layers of high resistivity ZNO. So, high resistivity ZNO has a rho of about 1 to 100 ohm centimeter, and this basically reduces the defect density at the interfaces, and this improves the diode quality. So, you can say it reduces the impact of defects in CDS layer as well as in CIGS, and it also provides protection to the interface. And it leads to increases the shunt resistance and hence reduces the leakage. So, these are some attributes of high resistance zinc oxide layer that we use in these devices. And then we have top contact. So, top contact in these cells is of so basically it is a metal contact, and you can have a aluminum grid on top, okay, and generally it is done through a shadow mask. So, if I just draw the structure of this device again, if you recall, the structure was like this. So, you had soda lime glass. So, this was glass, sodium containing glass, then we have moly, which is the back contact, then we have CIGS, then we have CDS. So, in this case CDS is deposited after CIGS is deposited. So, that is why when you deposit CDS on CIGS, the diffusion of the compound formation takes place at the interface, and CDS diffusion into CIGS may occur, and then we have ZNO, and then on top we have these metal contacts, which is, let us say, aluminum, or it could also be nickel. These solar cells have certain issues. The issues are number one, there is a poor short wavelength response, poor long wavelength response, spectral response, due to due to issues in carrier collection at the back. So, on the moly side, the carrier collection is poor, and this can be improved by grain boundary passivation. So, adopting appropriate heat treatment strategies by annealing. Okay. Then second issue that comes is high recombination in grain boundaries. At the grain boundaries, and heterojunction. Since it is a heterojunction, the recombination is more, and so basically the JD is higher than in polysilicon. So, this is an issue, and so these are certain issues in these solar cells, and so as I said, the efficiencies of these solar cells have increased to 21.7% approximately, with a VOC of nearly 0.718 volt and JSC of nearly 40.7 milliamps per centimeter square. This is at the lab scale. So, modules are lower, and this is made by Solar Frontier. Solar Frontier. So, but this is and there are also efforts to make solar cells on efforts to make CIGS solar cells on flexible foils. So, for example, in Switzerland, Professor A.N. Tiwari, he is leading. He is one of the world leaders in CIGS solar cells in Switzerland. So, a lot of work has been done. So, but it's a promising technology for future, and could be commercialized in near future. So, this is about CIGS solar cells that we have looked over past 1.5 lecture or so. Now, what we discuss is, we move on to just a quick overview of multi-junction solar cell. Before we go to Gen 3 technologies. Okay. Multi-junction is something which is which basically takes care of multiple band gaps within a structure, so that you can harness from long to medium to short wavelengths altogether, thereby increasing the performance of the solar cell. So, essentially the idea is to use, because in a silicon solar cell or in a CIGS solar cell, in CDT solar cell, there is only one band gap. So, which means any energy which is lower than the band gap is not going to be harnessed. So, if you can use multiple materials with varying band gaps in a stack, that offers you promise of using promise of giving you higher efficiencies. And for example, theoretically, if you can have infinite combination of band gaps, efficiencies can be as higher than 85%. So, that is where a lot of effort has been. So, basically it is about stacking of material junctions of varying band gap. However, while so efficiencies improve, increase, but processing also becomes very complex. So, example of this solar cell, for instance, is let us say we have a gallium arsenide substrate. So, this is so a lot of work has been done on multi-junction on gallium arsenide based substrates, because gallium arsenide is tunable. You can dope it with indium or aluminum, change the band gap, and as a result it is a very, so gallium arsenide or germanium substrate. On the back you put a metal contact. So, this is a metal contact of gold, and then we have on the top we have so we can say NP gallium arsenide bottom cell, okay, cell at the bottom, and this has a band gap of 1.42 eV. Then we have a PN tunnel junction. So, we have a PN tunnel junction, and then we have another top cell. So, we have a top cell which is of NP, let us say gallium indium phosphide, and this has a band gap of 1.85 eV, and then we put anti-reflection coating on top, and we put electrodes. So, we have these top electrodes. So, these are and we also have these anti-reflection coatings. So we put ARC and this is top contact. So this is how, so basically when the light comes, this absorbs short lambda and this absorbs longer lambda. So this is just two band gap. You can have multiple band gaps, and these solar cells give you efficiencies. If you look at the efficiency chart, efficiencies have crossed 40% now. So these multi-junction solar cells have efficiencies. So various combinations have given you efficiencies higher than 40%. But they are very expensive because making them is not easier. You need to have precise layers in between. You need to have you need to prevent the shorting of cells and so on and so forth. So if you as we saw earlier, that efficiency limit if you have infinite number of gaps, then efficiency limit is 86.6%. However, if you have one band gap, then we have 37% nearly. If you have two EGs, then we have about 50%. If you have three band gaps, then you have about 56%. If you have 36 band gaps, then it's about 72%. So you can increase this number very close to, and generally the way it is stacked is, so you have the first junction, then you have a separator, then you have second junction, then you have a separator, and then again. So this is how. So if your light is coming from this side, so let's say this is EG1, this is EG2, this is EG3, and so on and so forth. So EG1 is greater than EG2 is greater than EG3, and so on and so forth. So basically you are putting the highest band gap on top and lowest band gap at the bottom, so that short wavelengths are absorbed on the top and longer wavelengths are absorbed at the bottom. So for instance, we can have a combination of indium gallium phosphide, indium gallium arsenide, indium gallium arsenide, indium gallium arsenide, and indium gallium phosphide, indium gallium arsenide. This is a very good combination, 3-junction cell that can give you fairly good efficiencies in these solar cells. So multi-junction efficiencies, as we said, have exceeded have exceeded 40%, practically speaking. So before now the next lecture, in the next lecture, now we are going to start Gen 3 solar cells. So before we start the next lecture, let me just summarize now this part. So in Gen 2, so in the Gen 2, we first started our discussion with amorphous silicon solar cells. Amorphous silicon is a thin film solar cell which is based on PIN junction. So you have P silicon, you have I amorphous silicon, and then you have N amorphous silicon. All right, P and N are very thin, and A is the thickest layer, where I is the thickest layer where most of the absorption occurs, right. These solar cells give you efficiency of the order of about 10%. Then we looked at, so this was interesting technology at our time, but now it is not so much in favor. Then the second thing that we looked at was CDTE solar cells. CDTE solar cell is a technology which is wonderful technology because it gives you efficiencies more than 20% right now. It is a relatively simple technology to make, to fabricate. Material complexity is less because it is a binary compound of cadmium tellurium. So, material complexity is not so difficult, and it is a thin film device. And the structure that we saw, so in this case we had, so if you have a glass substrate, so this was glass, on top of glass we had a layer of let us say TCO, then we had a sort of high resistivity oxide layer, on top of this we have a cadmium sulphide window layer which is 50 to 100 nanometer, and then we had a layer of CDTE which is about 2 to 5 micron, and on top of this we had, so this is N type NCDS, this is P CDTE, this is what is PN junction, and then on top of CDTE we had a gold contact or nickel aluminum contact. Okay. So, in this case you can see that on top of oxide, on the glass we have TCO, on TCO we have oxide, then we have CDS, then we have CDTE. So, CDTE deposition is done after the CDS is deposited. So, here that is the difference you have to note, that cadmium telluride is deposited after CDS. It is a relatively simple structure. If you look at CIGS, that is what other technology that we looked at, CIGS efficiency is again more than 20% as of now. CIGS offers you very good band gap tuning by changing indium to gallium ratio. Okay. So, you can go from 1 electron volt nearly to slightly higher voltages. You do not go to very high VOCs, but the VOCs are very high band gaps, but you stay around 1.1 or so, that is what gives you the optimum performance. And this, okay, one more thing which I wanted to mention in CDTE. CDTE has important thing of cadmium chloride treatment. So, this cadmium chloride treatment is very vital to improve the performance of CDTE solar cell. So, in CIGS, as we were talking about, in CIGS, this is the, however, it is a compositionally complex material. So, phase optimization is complex. So, one needs to have right temperature, time and ambient to synthesize the correct phase, otherwise you end up forming the binary and ternary compounds which are not CIGS. So, you have to prevent formation of secondary phases, and these secondary phases are basically you can have IN2SE3, you can have GA2SE3 and so on and so forth, variety of these compounds can form. Okay. Selenium selenization is an important step which is also a safety issue, because dealing with selenium requires you to have safety protocols. So, safety is an issue here. However, nevertheless, CIGS is an interesting technology, and in CIGS you have glass, on top of this we deposit a moly contact, and on this moly we deposit CIGS. So, you can see that the difference here is that on glass we have moly, and moly is an opaque metal. As a result, CIGS is deposited on top, CDS is deposited on the top of CIGS. So, you can see that CDS deposition is after the CIGS deposition. So, this is the difference with respect to cadmium telluride. And then of course, you have a high resistance oxide layer, and then you have metal contacts. Okay. So, here the light comes from top. So, as a result, the optimization of top grid is important, just like in silicon. okay, because light cannot come from the glass slide because you have a metal electrode on top of it. So, here top electrode design is important. And then we looked at multi-junction solar cells, which are nothing but the combination of various band gaps, and or you can say these are tandem, so solar cells, or you can say tandem cells, in which you put in multiple band gaps in tandem and you increase the efficiency up to 40+%. So, between 40 and 50% have been achieved by combining various materials of different band gaps. So, this is what is summary of Gen 2 solar cells, and I have already told you the books, which books you have to go through. There are two good books, that is Handbook of Photovoltaic Science and Technology and Thin Film Solar Cells. These are two good books for learning about these solar cell technologies. So, we finish here. In the next lecture we will start our discussion on Gen 3 devices. Thank you.